Welcome to Sean White's Solar and Energy Storage Podcast. In this podcast, which is called Lithium-ion Battery Basics, we are going to cover C rates, hour rates, E rates. We're going to compare lithium to lead-acid batteries. We're going to talk about the DoD, and yes, that means depth of discharge and not Department of Defense. We're going to talk about battery cells, battery modules, battery packs. We're going to talk about series and parallel connections, the different types of lithium-ion batteries such as cylindrical, prismatic, and pouch batteries. We're going to cover cathodes and anodes. We're also going to talk about electron flow current theory versus the opposite direction, which is the conventional current direction. And we're going to cover electrolytes and the graphite anode. To learn more, go to solarsean.com. On with the podcast. Hey there. We're going to start off talking about C rates, and we're going to get into some of the battery basics. Really important stuff to get a good handle on, so put this in your memory banks. The C rate is a measure of the rate at which the battery is discharged relative to its maximum capacity. So actually, it's not a charge rate, but it's a discharge rate. That's oftentimes confusing, and it's very similar, the charge rate and the discharge rate. So why don't they call it the D rate, huh? Oh, because we already have D rating for wires. So it's called the C rate, and it's the discharge rate of the battery. A 1 C rate means that you could discharge the battery entirely within 1 hour. Typically, you're not going to discharge a battery entirely because you're going to discharge it not all the way, because discharging it entirely is not good for the battery. In fact, with lithium batteries, it's not good to fully charge the battery either. So a lot of times people with electric cars only fully charge their battery when they're going to go for a long drive. So if you have a lithium battery on your house, maybe you only want to fully charge that battery when you know the power is going to be shut off. Or if you're off-grid, maybe you only want to fully charge that battery when you know there's a big snowstorm coming. So a C rate of 2C, that would mean that you could discharge the battery completely in a half an hour, or at a rate of 2 times an hour. That would be a 2C rate, and that's kind of fast. And if you could discharge a battery 2 times in an hour, that's a good battery for power because you're letting it out all at once. You might think of things like power tools and things like that, where it's easy to discharge the whole battery within an hour. And now let's talk about the C/2 rate. Sometimes we see that with lead acid batteries especially, and that would mean 1/2 C rate. So if you discharge your battery at a C/2 or a 1/2 C rate, that means you could discharge half of your battery in an hour. And this is not always what you could do. A lot of times what we're looking at is the amp hours at different C rates. Because if you discharge a battery slower, you get more out of it, especially when you're talking about lead acid batteries. Lithium batteries are not as bad for losing energy when you discharge fast. Sometimes, once in a while, especially if you're talking to somebody at MIT, that's the Massachusetts Institute of Technology, you might hear about an E rate, and that would be the discharge power. So one of the things that's really confusing about C rates is when you're looking at the lead acid batteries, they give you something that a lot of people confuse as being the C rate. If you go to the auto parts store and look for your batteries there, you're often able to get very confused because the C20 battery capacity. And this really means the 20-hour battery capacity. So that would mean a C rate of 1 divided by 20. So like I was saying, sometimes it would say C/20, sometimes it'll even say C20, and that is not your C rate. That is the inverse of the C rate. This would be the 20-hour rate. So just be careful, and if your numbers don't sound right, maybe it's the inverse. Depends if you're a scientist or a mechanic.
In the face of overwhelming odds, I'm left with only one option. I'm gonna have to science the shit out of this.
Here's the math. The C rate versus the hour rate. So if you go 10 hours, that means you could charge your battery 1/10 within 1 hour. That's what that's all about. So just don't get confused when you go to the auto parts store and it's a little bit different than what you would see on a science-based lithium battery technical specification sheet. And if you're looking at lead acid batteries, it's kind of like the auto parts store. They're kind of related. They're lead acid. And remember, DoD does not just mean the Department of Defense. Although they use batteries, it also means depth of discharge. Okay, now we're going to get into cells, modules, and packs. And a lot of times when you're researching batteries, you're going to get stuff that has to do with electric vehicles. But since the electric vehicle industry is so successful, a lot of times we're using the same batteries that we use in cars and buildings and for large energy storage systems, just because mass production has brought the cost down so much. That's a good thing. So just remember cells, modules, and packs. It kind of reminds me of solar cells, solar modules, and solar panels. Panel starts with a P, just like a pack. So the cell is the smallest thing. It's like a battery cell. A module would be several cells connected together, perhaps series, parallel, or some combination thereof. And then a pack is connecting a bunch of modules together. Starts with a P, it's a pack, and it's a bunch of modules. And you can connect them together in series and parallel. So remember, series is positive to negative. Parallel is taking all your positives, connect them to one place, connecting all your negatives to one place. Series will increase your voltage. Parallel increases your current. Series does not increase your current at all. Parallel does not increase your voltage at all. These cells are connected together to make a module, and then these modules are connected together to make a pack. How neat. Here's a quiz for you. So what is the type of battery that is shaped like an elongated beer can? What do we call that? That's right. That's called a cylindrical battery. How about the one that is made with a rugged case, and it is the shape sort of a book? You remember what a book is, but it's a rugged case, a lot of times made out of metal. And that's right. You call that one a prismatic battery. Prismatic is made in this rugged case. And then how about it's sort of like in a Ziploc baggie? That's the kind of battery cell that you have in your phone or that LG Chem likes to use. That's right. That one is called a pouch battery. So we have cylindrical, prismatic, and pouch. So let's talk about some of these different types of batteries. Again, the cylindrical battery has high specific energy. It has good mechanical stability. I mean, you have those batteries in your flashlight. They're cylindrical. It has some good safety features such as venting. It's been around for a long time. It's like you had a big, long, flat battery and you just rolled it up like a cigar, except perhaps it's a little bit healthier than a cigar because lithium is not bad for you. Did you take your lithium today? I could tell you I took mine, right? The one thing that could be the drawback of a cylindrical battery, or you might hear from their competitors, is with the cylindrical battery, when you fit a bunch of circles together, you're going to have spaces in between. But perhaps we can use those spaces for cooling the batteries. Just like if you were in the solar industry, you see monocrystalline solar cells have rounded corners, so we're not using the entire space. Kind of a similar thing that we're dealing with cylindrical batteries. It's a nice, neat little unit. And now let's talk about the pouch battery. And it's just a laminated architecture in a bag. That's right, we have it in the bag. It's not very heavy because it doesn't have metal like you would see with the cylindrical or a lot of the prismatic batteries. However, it's cost effective, but there are some arguments against it, such as humidity and high temperatures shortening its life. But another thing that they brag about, like LG does when they're selling these batteries, is when it expands and contracts, it can expand and contract evenly, whereas if you had this rolled up in a cylinder, you might get some cracking and delamination. Now we're talking about prismatic batteries. Sometimes they say it is jelly rolled. A lot of times it's inside aluminum or steel, and it is sort of rolled like a cylindrical battery, but it's more efficient because it is more rectangular, so it doesn't have that problem with the rounded corners as much. However, if you went inside there, it is still rolled up, and these are very popular types of batteries. The prismatic battery. You know, the shape of a prism is kind of confusing because especially if you're a Pink Floyd fan like I have been throughout a lot of my life and saw them in concert a bunch of times, is you think of that triangular based prism that's refracting the light, but the prism of the prismatic battery is a different kind of a shape than that dark side of the moon prism. So just remember the prismatic battery is not really shaped that way because there's all kinds of prisms, including the prismatic battery. And when they say jelly rolled, that just means that inside they're rolling things up together. Okay, let's talk some internal battery parts. First, we're going to talk about the cathode. So when you're discharging, the electrons and the lithium head towards the cathode. When you're charging, the lithium and the electrons head away from the cathode. Another thing here that's a little bit confusing is it says the current is going the opposite direction of the electrons, and that just depends on your definition of current, so I would probably ignore that. But if you want to look a little bit deeper into there, if you take a physics class, they say the current is going the way of the positive. And that's because when they first invented the term current back in the day, they didn't know what an electron was. And so they just said, hey, it's going this way. So we have electron flow theory, which is the way the electricians look at it. And I kind of like that way because it just shows you which way the electrons are going. And the electrons, in some definitions, are going the way of the current. So discharging, lithium and electrons going to the cathode. The cathode is the positive pole of the battery. And when you're charging, what's happening is the lithium and the electrons are going away from the cathode. Cathodes are kind of important. Cathode determines the capacity and voltage of a lithium-ion battery. The cathode of a lithium-ion battery is the lithium oxide. The cathode is very important in determining the characteristics of the battery, such as the capacity and the voltage. It has to do with the active material used for the cathode. And so the anode has a potential difference that is small. So that has to do with voltage. When we talk about potential difference between anode and cathode, the potential difference for cathode is higher and plays a significant role in determining the voltage of the battery. So I like to say that the cathode is the positive pole of the typical battery, and the cathode, since it's positive, has the third letter in cathode is T, and it's sort of like a plus sign. And so that's a good way to remember that cathode is positive. There are some exceptions to this, but in general, most things that you're going to be using, that cathode is the positive pole of the battery. Now, anode, the second letter in anode is N, and that N is for negative. And so the anode will let you absorb lithium ions that are released from the cathode as you're charging the battery. So you're charging the battery, and these lithium ions are absorbed by the anode. So a charged battery has lithium on the anode, a discharged battery has lithium on the cathode. Lithium ions, so that's like lithium in solution, that goes between the cathode and the anode, depending if you're charging and discharging. Then you have an electrolyte, and that electrolyte is sort of like a semi-permeable membrane that lets the lithium ions flow through, but not the electrons. Typically, in most all lithium batteries these days, the anode is a graphite anode. Graphite is made out of carbon. It's what they made a lot of pencils out of after they figured out that lead was not a good idea for pencils unless you want your kids to lose brain cells. Now we're going to talk about the electrolyte a little bit more. And so electrolyte, it facilitates the movement of lithium ions between the cathode and the anode. So it's like some place where these ions can swim. And the most commonly used electrolyte is a lithium salt. So we're not talking sodium chloride, something that you sprinkle on your eggs. We're talking about a different type of salt. That's the chemistry term. And one of these salts would be lithium hexafluorophosphate in an organic solution. That sounds tasty. But there's a lot of different ways that you can have an electrolyte. Sometimes you hear people talk about solid state electrolyte, which means it's not a liquid at all. Think of an analogy there where you have gel batteries when we're talking about lead acid batteries. So that would be an electrolyte that's not a liquid, it's a gel. And now getting a little deeper into the separator, it's a physical barrier that keeps the anode and the cathode apart. It prevents the flow of electrons and allows only lithium ions to pass through internal microscopic holes. Those have to be really small holes, and typically you will have a synthetic resin like polyethylene, kind of means plastic, and polypropylene. I can remember my grandfather, who was a scientist, and instead of saying plastic, like bring that plastic over here, he would say, can you bring that polyethylene over here, please? So we have the same thing, polypropylene, and that's just a harder plastic. So pretty much just know that your separator is usually plastic with holes in it. Usually you don't want holes in your plastic. However, we want microscopic holes in our separator with our lithium-ion batteries. I hope you learned about C rates and all of these battery basic terms. Thanks for listening to Sean White's Solar and Energy Storage Podcast. Get smart and have fun by going to solarsean.com. Thank you, and over and out.